Hi everyone. Today we are going to discuss about the effects of electric current. Electric current has the following effects. One is magnetic effect, heating effect, lighting effect, mechanical effect, chemical effect. Today we are going to discuss about magnetic effect, heating effect, lighting effect and mechanical effect. It was a time when electricity and magnetism was two different concepts. Later, Hans Christian Ørsted, a Dutch physicist, was doing an experiment to explain about the concept of electricity, wherein he had kept a needle near the electric circuit. It suddenly deflected, and the following thing happened, which I am going to demonstrate here now, and you will observe. You observe here a rod, that is aluminum rod running here, through which the current flows, and a magnetic needle is kept below it, which is not in contact with it at any cost. Now, if at all I pass current through this, you have to observe what happens to this magnetic needle. The magnetic needle deflects. Now, I reverse the polarity of this. Now you observe the deflection. This time the direction of deflection is in the other way around. I repeat this experiment again. It was initially positive to negative. The current is flowing in one direction. It deflects towards left. Now I reverse the polarity and pass the current in the other direction. You can see the deflection towards the right. Now, what is the cause for this deflection? The cause for this deflection is, whenever a current is flowing through a conductor, we know there are moving electric charges. The moving electric charges has both magnetic field and electric field. So, Ørsted concluded that whenever there is a current carrying conductor, there is also magnetic field in it. And it also has, we can see a magnetic needle here, it also has a magnetic field of its own. So there are two magnetic fields which are in interaction, which creates a force there, and therefore they repel each other. And as we know, the repulsion is the sure test for magnetism. They both interact and they tend to deflect. The magnetic needle tend to deflect. The direction of deflection is different because the polarity, the direction of magnetic field also changes, and hence the deflection varies. That can be understood by observing this diagram. Now, if at all you see, the positive terminal is connected towards the right, and the current is moving from south to north. Now the deflection is towards the west. So this I can conclude by just giving a mnemonic like snow rule. What does this say? When the current flows from south to north, S for south, N for north, south to north, over the conductor, the deflection is towards the west. I repeat, when the current flows from south to north over the conductor, the deflection is towards the west. Similarly, if the current moves from north to south by reversing the polarity, the deflection is in the other way around. That is, when it is from north to south over the conductor, deflection is towards the east. So to just remember, we have this particular snow rule. Now, in order to understand the effects of magnetic field, that is the strength of the magnetic field, we have a straight current carrying conductor here. Now we will discuss about the direction of deflection. This can be given by, if at all we imagine a person swimming, and if the direction of swimming is along the current is along the direction of swimming, the deflection is towards his left hand. You can observe his left hand and the deflection is towards the left hand. If I reverse the polarity, the current will be in the other direction, and if at all this shows the swimmer is in the opposite direction, now the deflection is towards his left. This rule was given by Ampere and hence it is called Ampere's swimming rule. Now let us move on to the next experiment on the magnetic field around a straight current carrying conductor. We have just concluded by Oersted's experiment that every current carrying conductor has a magnetic field around it. Now we will see around a straight current carrying conductor how the strength of the magnetic field varies as well. For which we have a straight current carrying conductor here, and I have iron filings with me. I sprinkle iron filings around this straight current carrying conductor. Now I switch on, I pass the current through the straight conductor and gently tap it. Now you can see the concentric circles around the straight current carrying conductor. What is the reason for this concentric circles? It is because the magnetic field is around the current carrying conductor and it is aligned in the circular pattern. Now the strength of the magnetic current carrying conductor depends on the amount of current that is passed through it, the distance from the current carrying conductor. As the distance increases, the magnetic field decreases. Now we can also, the direction of magnetic field can be understood by using right hand grip rule. This says if at all the current is along the direction of the thumb, if at all we hold a current carrying conductor such that the thumb shows the direction of current, the fingers encircling the direction shows the direction of magnetic field. Now we can even demonstrate this using the magnetic needle, magnetic compass. I have kept magnetic compass here around the conductor, and later you can observe the direction of the deflection of the needle. They all deflect in this direction in which the fingers is encircling. If I reverse the direction of current, the deflection will be in the opposite direction. So this is about the straight current carrying conductor. My question is, why should we tap the board for aligning? The answer is that the iron filing particles tend to hold by the friction of the board. In order to overcome that, we have to tap the board so that in the weak magnetic fields they would have aligned, and once they get tapping, they overcome the static friction and they align themselves in the direction of the magnetic field. So this is about the straight current carrying conductor. Next, we will move on towards the circular loop. In a circular loop, now wait a minute. In a circular loop, I have connected here between 0 to 50 turns. This is a circular loop between 0 to 50 turns. Now I will connect a magnetic needle here. You can observe it also comes to rest in north-south direction. I pass the current and you can see the deflection. It deflects towards the right. So I reverse the polarity. Now you can see the deflection of the north pole. What happens? It is deflection towards the left. Now what does this say? This is called the clock rule. The clock rule says, if at all the current is flowing in a clockwise rotation, if the current flows in the clock rotation, the loop facing towards the students, it will be the south pole, and the other side would be, for example, if it is AOB, the direction facing the AOB towards the U people, it would be south pole. If it is anti-clockwise, then this would be north pole. It is north pole. So therefore, the two poles which are created are south pole and north pole. Now this is called as the clock rule. Now we will observe the magnetic field pattern around the circular loop. I sprinkle the iron filings here. Now I would pass the current through it for about 30 seconds and I gently tap it. You can observe this beautiful pattern in which the circular, near the conductor it is circular, as and when it moves away from the conductor it becomes parallel. At the center it is absolutely parallel, and here it is changing its direction. It is the anti-clockwise direction or clockwise direction. It depends on the direction of the current which is passed. This is the pattern around a circular coil or circular loop. Now we shall discuss on the factors on which the magnetic field depend, for which I use the protractor. Before that, I have to clean this iron filings, else it gets attracted to the magnetic needle